Welcome. In this video, we'll be looking at geometric modeling, in particular compound interest and reducing balance depreciation. So before we get into this, I would recommend prior viewing of the following two YouTube clips, the links to which I will place in the comments under this video. So let's look at two different scenarios today. Scenario 1, James has $1,000 that he wishes to invest at his bank. The bank offers James the following terms: an interest rate of 5% per annum compounded annually. Task number 1, write a recurrence relation to model this investment. So let's work out the general relation. For recurrence relations involving compounding interest, we have, as always, a term, Vn, a value at some particular time, and then the next value, the next year, Vn plus 1, the next term. So this is worked out when we're looking at compounding annually. We're no longer adding a common difference as we were in our flat rate arithmetic modeling. With geometric, we're multiplying by a ratio or a factor. So of course you have a rule and an initial state. So step 2, let's calculate the growth rate R for this compounding interest. So the rate was 5% per annum, and we want to work out what is this growth rate. So here's our equation. What we do is we take our rate and our percentage, we divide it by 100 and we add it to 1. So what was 5% generates a growth rate of 1.05. The 5 over 100 effectively moves the decimal place 2 to the left. So our growth rate for this particular recurrence is going to be 1.05. So let's substitute this into our general rule. Here's our general rule. And now we have a rate of 1.05 with an initial value of $1,000. And that was our principal being invested. So the recurrence relation to model this investment is Vn plus 1 equals 1.05, the growth rate, multiplied by Vn, the previous term, with an initial starting value of $1,000. Task 2, what's the value of the investment after 3 years? So the initial value of this investment, when we first invest, is $1,000. The value after 1 year is this $1,000 multiplied by the growth rate or the rate factor of 1.05. That gives us a return of $1,050. This is the same return after 1 year of a flat rate investment of 5% per annum. That's where our similarities stop. What happens now to work out the value of the second year is we take this value of the first year, 1050, and we multiply that by our growth factor of 1.05. So it now returns, after the second year, a return of $1,102.50. Effectively, we've gained interest on our interest, hence the word compounding. So the returning interest in the second year was $52.50. Finally, for the third year, we take this value at the end of the second year and we multiply it by our growth factor of 1.05, and that gives us a return of $1,157.63. The returning interest on this particular year was $55.13. So after 3 years, James's investment will be worth $1,157.63. This can, of course, be calculated using the TI Inspire CAS calculator. We enter our V0, or our principal value, as $1,000 and press enter. We then multiply it by 1.05, our growth rate. And we do that for 1 year, 2 years, 3 years, which gives us an investment return after 3 years of $1,175.63. Task 3, how many years would it take for James to double his investment? Once again, this is easier to model using the CAS calculator. How many years would it take Jamie to double his money? Well, he starts with a principal of 1,000. We press enter. And then we're going to multiply that by a growth rate of 1.05, effectively a 5% per annum compounding annually. So we want to go from 1,000 to 2,000. Let's count this out. 1 year, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in the 15th year, the balance of his account would have doubled to in excess of $2,000. So as we just discovered, James's investment would double in value during the 15th year via this compounding interest model. Task number 4, write a rule that will calculate the value of James's investment after n years. We saw from our previous example that using a linear recursion can take considerable terms to calculate some future value. Let's find a simpler way using a general rule. So a general rule takes this format where we can work out the value of the nth year, the nth term, if we know its initial value, its growth rate, and the number of years. So let's again very quickly work out the growth rate, which we've done previously. The rate was 5%, little r, and we want to work out the growth rate, capital R. So growth rate equals 1 plus little r over 100. In this case, it was 5%. So 1 plus 5 over 100 gives me a return of r equals 1.05. So the growth rate for this model is 1.05. Sub that into our general rule. So to calculate a predicted value of this investment after n years, we're going to take our 1,000, our initial value, multiply it by a growth rate of 1.05, raised to the power of n, the number of years. So that's our rule. Vn equals 1,000 times 1.05 to the power of n. Task number 5, let's use this rule to calculate the value of the investment after 15 years. So we want to know what is the value of this investment, subscript 15, after 15 years. So the initial value after 0 years at the start was $1,000, and we now have an n of 15 years. The number of years is 15. Here's our rule that we just calculated. The future value Vn is equal to 1,000 multiplied by 105 raised to the power of n. So the value of after 15 years will be 1,000 times 105 to the power of 15. N is for 15 years. So that gives us a return of $2,078.93 after 15 years under these investment terms. So after 15 years, James's investment will be worth $2,078.93. Task 6, at what year will James's investment reach $1,400? So some future value after n years, it will reach $1,400. Our initial starting value or principal is 1,000. We want to calculate n. How many years will it take to go from 1,000 and increase to 1,400? Here's our rule that we used previously. So we've substituted in our value after n years, a future value of 1,400. We started with 1,000. It's being increased by this growth rate of 1.05. We want to work out how many years n will we need to raise this to the power to get a value of 1,400. We can, of course, use our solve function on our graphics calculator. So let's turn to our TI Nspire CAS calculator to solve this problem. So I've entered our equation into the solve function, and that returns the number of years of reaching $1,400 as 6.89631. So in the 7th year, this investment of $1,000 would have reached $1,400. As we saw using the CAS calculator, it would take 6.89631 years for James's investment starting at $1,000, gaining interest at 5% per annum, compounded annually to reach $1,400. So during the 7th year, James's investment has reached a value of $1,400. Let's now have a look at graphing this compounding interest model. In this list in spreadsheets, I have in column A the years of investment, and in column B the value of the compounding interest. Okay, this value was determined by using the following formula. Value with the compounding interest is equal to 1,000 times the growth rate of 1.05 raised to the power of the number of years, where the number of years is represented in column A. Let's have a look at this graphically. Let's plot ourselves a graph. Here's our value of compounding interest and our years. You can see a nice curve being formed here. The main feature is at 0 years we have an investment of $1,000. After 1 year, that's gone up by 50 to 1,050. Now if we look at the difference as we go along now, so from 1,050 we jump to $1,102.50. So that's gone up by 52.5. It's increased the difference. At the top here, we've increased from 3,920 to 4,116. The difference between each term is getting bigger and bigger. This is typical of a geometric sequence. Let's compare the value of the compounding interest graph against the value of a simple interest graph that we've used in a previous video. The simple interest calculation starts off with a value of 1,000, and we're going to add to that $50 multiplied by the number of years. Okay, so in a simple interest, it starts at 1,000, we add on 50, 50, 50, 50 continuously. Let's see what that looks like as a comparison with a graph. Let's go. We want compounding interest. Add to that the years. There's our gradient. And if we can, we want to also add another y variable for simple interest. This gives a good comparison. We can see here with the simple interest, it goes up from a starting value of 1,000. up by 50, by 50, by 50. It is the same increase the whole way along that particular relationship. This is a straight line simple interest relationship, whereas our compounding interest has an increasing difference between each term in the sequence. And that's because it's being multiplied by a factor rather than being added by a difference. Scenario 2, James buys a brand new sports car for $60,000. Off he goes. James's car depreciates with a reducing balance depreciation of 2% per annum. So task 1, write a recurrence relation to model the reducing balance depreciation. So step 1, we look at our general relation. So again, the value of the next term is equal to the value of the previous term multiplied by a growth factor and an initial value of V0. Let's work out our growth rate or a growth factor for this particular recursion model. So R is 2%, and we want to calculate what is capital R for our model here, our growth rate. So in this case, we're depreciating. We're going down in value. So instead of having the growth rate is equal to 1 plus R over 100, as we did before when we're looking at our compounding interest, now we're taking away our rate, our depreciation rate of 2%. So that will be 1 take away 2 over 100, which gives me a growth rate of only 0.98. It's actually going to stunt the growth. It's going to decay and make it smaller. But that is the idea of a reducing balance depreciation. Let's substitute these values into the general rule. The value of the next term is equal to the value of the previous term multiplied by its growth rate or growth factor with an initial value. So here we have our growth factor of 0.98 and an initial value of 60,000. So the recurrence relation to model the flat rate depreciation is Vn plus 1 equals 0.98 times Vn, where the initial value was $60,000. Task number 2, what's the value of the sports car after 3 years? So the initial value of the sports car, V0, was $60,000. After 1 year, we would take that $60,000 and multiply it by the growth rate of 0.98. That will reduce it down to $58,800. The value of the sports car after the second year, we take this value, V1, and we multiply it by the growth factor of 0.98 to calculate V2. That will reduce it to $57,624. And finally, we take that value and we multiply it, V2 that is, by our growth rate of 0.98, and that will further reduce it after 3 years to $56,471.52. So, after 3 years, James's sports car will be worth $56,471.52. Let's model this calculation using the TI Inspire CAS calculator. So first of all, our initial value is 60,000, enter, and we're going to multiply that by a growth rate of 0.98, meaning it's going to reduce by 2% each year. So after 1, 2, and 3 years, we find the vehicle's value after 3 years under these reducing balance depreciation arrangements is $56,471.52. Task number 3. How many years would it take for the value of James's sports car to halve? Well, again, this would be a lot quicker using the TI Inspire calculator. We start with a vehicle of initial value $60,000. We return that, and then we're going to multiply it by a growth rate or growth factor of 98%, which represents a 2% reduction every year. Let's see how many years it takes, drop down to 30,000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5. So it's in the 35th year that this vehicle will reach half its value from $60,000 to $30,000. So we found that James's car would half in value during the 35th year using this reducing balance depreciation model. Task number 4, write a rule that will calculate the value of James's sports car after n years. Clearly from our previous example, we see the benefit of using rules rather than recursion models for a larger number of terms. Step number 1, write out the general rule. So here we have our value after n years is equal to our initial value multiplied by the growth rate to the power of n. Step 2, we've already calculated the growth rate previously, but we'll do it again. R, the reducing balance depreciation rate, is 2% per annum, and the growth rate will equal the following: 1 take away R over 100. R equals 1 take 2 over 100, which gives me a growth rate of 0.98. So, write a rule that will calculate James's sports car after n years. Let's substitute our values in. Vn, the future value after n years, will be equal to 60,000 multiplied by 0.98 to the power of n, where n is the number of years. The rule used to calculate the value of James's sports car is as follows. Let's now use this rule to calculate the value of the sports car after 10 years. The value, subscript 10 after 10 years is question mark. Value, subscript 0, the initial value is $60,000. And n equals 10 for 10 years. Here's our equation that we just determined. So the value after 10 years would be 60,000 times a growth rate of 0.98 raised to the power of 10. Doing that, we find the value of the vehicle after 10 years is $49,024.37. Task number 6. At what year will the value of James's sports car depreciate to $40,000? So we want to know the value in some future year n where it reaches $40,000. We know its initial value, V0, is going to be 60,000, and n is a question mark. What year will it take for this to depreciate to 40,000? So here's our expression. So Vn, the future value after n years, will be 40,000. It's initially equal to 60,000, and we'll multiply it by a growth factor of 0.98, and we're trying to calculate n. After how many years will it drop from 60,000 to 40,000? Now, the solve function on the TI CAS calculator is probably the best way of solving this problem. In fact, it would take quite a lot of mathematical manipulation to calculate n otherwise. So let's turn to our TI Inspire CAS calculator to solve this problem. Here's our solve equation. We're looking at the number of years it takes using this reducing balance arrangement for this vehicle to drop from $60,000's original principal value to $40,000. We place in the solve function, and that tells us the number of years required is 20.06. As we found, it was during the 21st year that James's sports car would depreciate to a value of $40,000. It happens just after the 20th year, but it's in the 21st year. Finally, task number 7, we wish to graph this reducing balance depreciation model to compare it against the flat rate depreciation model. So in this list in spreadsheets, we have the years from 0 counting upwards, and we have the value of the reducing balance depreciation. So at our initial purchase, after no years, we have the vehicle at $60,000, and then it starts to depreciate at a rate of 2% per year, reducing balance depreciation. See what this looks like graphically. We want the reducing balance depreciation against the years. Okay, so there's a curve as we go along. You can see here there's a greater reduction in the first year from 60,000 down to 58,800. That 1,200 is a gap. Compared to at the end here, this goes from 3,478 to 3,397. It's a smaller difference because it's only taking a percentage reduction of the previous. It's a curve shape. Let's now look at what happens when we compare that to the flat rate depreciation. Okay, so it's reducing by $1,200 every year in a flat rate depreciation. Let's see if we can plot this one. So again, we had originally the reducing balance depreciation on the vertical axis. We had the years on the horizontal. Now add another y variable. So we want to go the flat rate depreciation. Okay, you can see what happens here. In the flat rate depreciation, we're dropping by 1,200. We started at 60,000, it drops down to 5,880, and it continually drops by 1,200. It is a flat rate constant gradient. Whereas the reducing balance depreciation is dropping off less and less with each subsequent value in the sequence, because it's only being reduced by 2% of the previous value. You get a curve shape for the reduced balance depreciation and a straight line for the flat rate depreciation. Thank you for watching this video. I hope you've gained some insight and understanding in terms of compounding interest and reducing balance depreciation using the geometric sequencing modeling. As always, if you enjoyed this video, please like, share, comment, and subscribe. Thanks for watching.